our first review session, 8.1, explanation for questions in quiz 4. Yeah. I already opened up the answers, but here I like to explain those answers. Okay, all right, yeah. Let's look at the first question. Which of the following sorting algorithms is not an in-place algorithm? First, you need to understand the meaning of this in-place algorithm. Yeah, I gave you the definition when I talk about the quicksort, the partition step in quicksort. Yeah. Here, the meaning, so do not confuse it with another in-place meaning, but that one is for talking about elements in an array. Elements in an array are in place. We have special meaning for it. Yeah, we know that. But this one, yeah, we just learned, yeah, many of you may not be familiar with this in-place algorithm talking about extra space. Yeah. When we implement our algorithm, we need to use space, right? But some space we treat as extra space. Yeah. Yeah. Because the input data, we need to use storage space to store in-place data. So that's the normal part. Nobody can, save any space on the input data. So you have to store it with certain amount of space. So you do not count this storage space. But in order to implement your algorithm, you need extra space. Yeah. And sometimes some algorithms could use a lot of extra space. Then those algorithms we feel could be improved. There is a possibility to reduce extra storage space. Yeah, but this in-place algorithm, the extra space used is very little. Can be described as bigger of 1, this little, okay? Just bounded by constant multiple of 1. Yeah, 3, 4, 5 locations, even 10, 20, 100, yeah. But it must be a constant. Yeah. So when you increase the data size, when you increase the data size and increased, but extra space still bounded by a fixed number. So this kind of algorithm we treat as in-place algorithm, right? Yeah. Now we use this understanding to look at these 4 options. Selection sort. The extra space we use for swap. So here, most of the examples, when we look at extra space, we use for swap operation. Okay, yeah, swap operation. So selection sort, we just need 1 extra space for the swap operation. So it is in place, okay? Yeah, but here we need to find not in place, okay? So selection sort is in place algorithm, so we do not select it. Bubble sort, yeah, we only need to do swap operation, okay? Yeah, so it is in place, we do not select it. Insertion sort, also swap operation, 1 extra storage location, it is in place. Now, But the merge sort, you can see merge sort. You think about if we go back to the implementation details, divide and conquer. Okay, we need to copy our data to some auxiliary array. Think about that. Auxiliary array. Now, because otherwise it's hard to implement that merge operation. Okay. So consider that merge operation. That operation, the extra space you need to use, big O of n. This much space. Big O of n. So that's not big O of 1. Yeah. So the merge sort is not in place. So our selection is merge sort. Yeah. That's the first question. All right. Second one. When a given array is almost sorted, that's the main property we have here. Which of the following algorithms is the most efficient to sort this array? We learn this property when we learn the insertion sort. After we complete the insertion sort, we discuss. So under what situation the insertion sort is the best? This is the best case. We should use the insertion sort. Okay, yeah. Almost, yeah. So I drew a diagram. Suppose this is an array, almost sorted, but there are some scattered location. Yeah. Only a few places. Yeah. Small amount of data at these places unordered. If we need to sort this kind of data, then insertion sort is the best. Yeah, because it would give us the efficiency close to bigger of n. Close to, yeah. A little worse than that, but very close to that. Okay, very close to it. Yeah. But for others, much worse than this. Okay. So selection sort bigger of n squared, merge sort bigger of n log n, and quick sort also bigger of n log n. Oh, sorry, quick sort, yeah, because here we talk about worse. Almost sorted. Yeah, almost sorted in this situation. Not that good. Not that good. N squared. Quick sort. Yeah. So insertion sort is the best in this special type of data. Although it's rare, but in case you have this type of data, always think about this merge sort. Oh, sorry, this insertion sort. Yeah. All right. Yeah. Next question. Number 3. Yeah. Suppose that we have an ordered array and we want to do the binary search on it. If we know that the best case efficiency is 1, yeah, because at the root, right? At the root, you only need to do 1 comparison. All right? And the worst case efficiency 11, yeah, the bottom level, the bottom of the binary tree. So you need 11 comparisons. Question, can we say that the average case efficiency is 6 comparisons? Yeah. Here, I try to confuse you a little bit with this ordinary average formula, best case plus worst case divided by 2. Be careful, this way to calculate average case efficiency is wrong in general. Okay? Is wrong in general. Most of the case, it is wrong. Yeah. Only in some very special case, it is correct. Yeah. The reason is simple. The reason, the best case, worst case, and all other different cases, they are distributed unevenly for different levels of cases. Here, let me describe a typical binary search case. So we need to draw a binary tree for the binary search. So there are many different levels. At each different levels, we do different number of comparisons. Okay, yeah. Sometimes the tree could be like, like that. Okay, it's possible, the tree could be like that. All right, yeah. So here, look at the levels, all right, different levels, right, different levels. Okay, all right, yeah. So let me draw another level here. All right. Top level, you need to do one comparison. Next level, two comparison, and three, and so on. All right. Look at the number of nodes in different levels. They are distributed unevenly. Yeah. The higher the levels, the fewer the number of comparisons, but the number of nodes also fewer, right? When you go lower and lower levels, you have more and more nodes. Yeah. Although the bottom level, so usually the number of nodes could vary. Yeah. Sometimes big, sometimes small. But when you take the average, definitely you cannot do 1 plus the worst case, bottom level, that's the worst case. You cannot do that. 1 plus the worst case divided by 2. Yeah, in general, it is wrong. Yeah. So you have to consider the distribution. You have to count the number of nodes in each levels. Okay, so when you do calculation, so you need to count the number of nodes at each level. All right, yeah. So then take average. Okay, yeah. Based on your counting numbers, right? Yeah. Then, yeah. The number, it's hard to predict, right? Because you do not know the structure of the binary tree. Yeah. The structure is determined by the n number. Yeah. You have n nodes. Yeah. The value n is closely related to the structure of the n number. Okay, yeah, yeah. All right, yeah. So let's move to the next question, number 4. All right, yeah. Okay, here, all right. Yeah, and right here. All right. After we apply partitioning step in the quicksort, we can guarantee that at least one element is in place. True or false? Answer true. Yeah. The reason is the pivot, right? We have that special pivot element. So the pivot element must be in place. at the end of the partitioning. Okay? At the end, you do one swap operation, one possible swap, yeah, because there is a very special case. Yeah, the pivot already in place, so you don't need to do swap. If it is not in place, the last step, you need to do one swap operation to put it in place. Yeah. So that's the minimum number of swap. Yeah, the minimum, yeah, minimum could be 0. Yeah, no swap. Yeah, we have another question, related question later. Yeah, but other than that, non-swap one, yeah, the next one, you need to do one swap operation to put it in place. So this statement is correct. All right. Number 5, when we do the partitioning step in the quicksort, is it a good idea to use the median as the pivot? Yeah. Answer is no. Let me explain it. The answer is no. Okay? Yeah. Why? Because if you only look at the partitioning step, we know if the pivot is the median, then your partitioning would be the most balanced case. Most balanced case, right? Yeah. Yeah, because the two subarrays divided by this pivot element almost have almost the same size. Yeah. Then when the data is distributed evenly, we know it should correspond to the best case, right? Yeah. But there is another factor, important factor you need to consider. Yeah. Do not ignore this factor. That is the cost to find the median. That cost is pretty high. Okay? Because how do you get a median? Right? Think about it. So is it a good idea? If you say good idea, but you need to know how to find a median. Given an array, nobody knows its median, right? You need to find it. Yeah. The best algorithm to find a median still need big O of n, this much cost. That is the cost you need to pay to find the median. If you spend this much cost to find a median and then use the median as the pivot, although you have some gain, right? But the gain is too little comparing with this relatively high cost. This cost is pretty high, but the gain is much less than the cost you pay. Okay? Yeah. In other words, your total partition cost is much smaller than this median cost. Yeah. Partitioning, actually, the cost is not that high. The partitioning cost also big O of n, but even we compare big O of n, that one still smaller than this median big O of n. Yeah. Median is a, larger constant multiple than the partitioning that big O of n, the constant used in that big O of n. Now, so when you put these factors together, then the answer is it's a bad idea. Yeah, it's too expensive. Never think in that way. Okay? Yeah. So so at the end, we just use the randomly selected element, whatever we have at the last position of the array, we use it as the pivot element. It's much better than we try to find some special element in the middle as the pivot. Yeah. Yeah. All right. So that's question number 5. Yeah. Number 6. When we apply the quicksort on an array that has been already ordered. Yeah. So think about this case. Already ordered. Here, I do not say ascending, descending. That means ascending. Okay. Yeah. If we say order, descending order. Yeah. First, we treat it as unordered. Yeah, because descending, we need to make it ordered. We need to make it ascending order. Yeah. All right. So the ascending already ordered. We will get the best case efficiency. Actually, it's false. We get a worst case efficiency, not the best. Yeah. For different sorting algorithm, the behavior is different. Okay. Yeah. If the data already sorted, if you consider insertion sort, then you have the best case. Okay, yeah, for the insertion sort. But now we consider quick sort. Then already sorted, it looks like we do not need to do anything, right? Already ordered. The cost should be small, right? It is already sorted. The cost should be small, but actually, if you look at the details in the quick sort, that's not the case. It's the worst case. The worst case, that means its efficiency is bigger of n squared. Yeah. Why? So let me give you the, the main reason why it is the worst case. Yeah. The reason is simple. Yeah. The reason comes from you look at the partition. In the partition step, we split. We do split, right? Yeah. We do split on the data. But when we do the split, okay, yeah, the ordered case, the ordered data would give us most unbalanced split. Sorry, unbalanced split. Yeah. How to see that? Yeah, it's simple. Okay, so this is the array. Yeah. And the last element is the pivot, right? Yeah. Here we use the, this implementation. Yeah. Then think about when we compare all the elements with the pivot, they are all less than or equal to the last element. So we put all the remaining elements in one side of the pivot. Okay? Yeah. The other side, the right-hand side of the pivot is nothing. The right-hand side of the pivot is empty. Okay, so you can see the split is the most unbalanced at the two sides of the pivot. If it is unbalanced, then when you use divide and conquer, every time size reduction is very small. Yeah, you look at the size reduction. Size reduction. How much size reduction? You have one reduction. Yeah, just pivot. Every time when you do one partition, you reduce your data size by one. Just that pivot number, you reduce that. Okay? That reduction is too slow. Okay? Yeah. Then after you complete all the partitions in this way, that's the slowest. You get a bigger of n squared. Yeah. So you have the worst case, not the best case. Yeah. So you need to be very familiar with the partition step of the quicksort. Then you can answer this question. Yeah. Otherwise, I believe some of you just based on your intuition. Yeah. Your intuition works well for the insertion sort, but not for the quicksort. Yeah. Insertion sort, if I ask you this question, your answer is true. But now, the implementation details completely different for the quicksort. So your answer here should be false. Okay, yeah. From this growth function, yeah, if you can imagine the growth function, yeah, you can also see it is the worst, slowest. Yeah. All right, number 6. Number 7, yeah. Which of the following sorting algorithm has the property that its worst case efficiency is in n log n? Yeah. So here, this question we want to know for some of the sorting algorithms, the worst case is under control. Won't be n squared, bigger of n squared. So that's too bad. So we want to know those sorting algorithms. Here, I only give you one. Yeah, actually, we have several. Yeah, because the heap sort also has this property. Yeah, but here, because when you took this quiz, we haven't learned quicksort. Yeah, so I didn't put quicksort here. Sorry, heap sort here. All right. Yeah, so the worst case, yeah, for all these 3 options, the worst case all bigger of n squared. Yeah, only the merge case, the worst case is bigger of n log n. Okay, answer is this one. Why is that, right? Yeah. Okay. So we always want to ask us why when we answer one question. Yeah. The reason is simple. Think about when we do divide and conquer for the merge sort, how do we split the data? We split the data evenly, right? The answer is simple, because we always split the data evenly. Yeah. Because of this special operation, yeah, divide operation, the special one, yeah, our data is always distributed evenly. That means the worst case is well under control. Yeah. The worst case happens, the main reason for the worst case is the data is distributed in some unbalanced way, really bad unbalanced way. And the consequence is, much slower efficiency. Yeah. But the merge sort is designed to avoid unbalanced data distribution. Yeah. So that's the main property of the merge sort. So as a result, it can avoid very bad worst case efficiency. So we can enjoy this very good worst case efficiency. Yeah. All right. So the good thing for the heap sort here, because now we have learned the heap sort. So we want to put the heap sort in the same category. Heap sort has also this property. Yeah, because the heap sort, you can see its structure. So why heap sort has this property? Because the structure, the heap is a near complete binary tree. That's the structure of a heap. Near complete binary tree. What does this give us? Because the complete, look at that. The complete binary tree is most balanced binary tree, right? Yeah. Because the binary tree, sometimes it is balanced, sometimes it is unbalanced. What is the most balanced binary tree? A complete binary tree. That's the most balanced binary tree. But heap, we cannot guarantee it's a complete binary tree, but we can, we can make it close to a balanced binary tree. So that's near complete binary tree. Very close to the most balanced binary tree. So with that property, its worst case can be under control, and as a result, its efficiency is big of n log n. Yeah, we proved it. Yeah, we proved it. Okay, and our proof is very simple. Yeah, yeah, we have a quick proof of that. Okay, yeah. All right, so here I just connect to the heap sort. Number 8. When we use the divide and conquer view to understand merge sort, which of the following steps is trivial? Yeah. Here, some students ask me the meaning of trivial. Trivial here means we almost do nothing. Yeah. We do very little. Yeah. You may need to do something, but how much do you mean very little? Almost nothing. Bigger of 1. The operation you do bounded by some constant number. Yeah. So that's the minimum you can ask for. Yeah. All right. Yeah. So for the merge sort, when we do divide operation, we split in the middle. That step, we do very little, right? Yeah. That step, we do very little. Okay. Yeah. Combined step, we do a lot. Yeah, combined step, the merge operation, bigger of n. So that's a lot. Okay, a lot of work. Yeah. But divide step, just use certain index number to control the left subarray and the right subarray. The index range for the left subarray and the right subarray. That's it. So that's very little amount of work. Yeah. All right. Last 2 questions. Number 9. when we apply the quicksort on a given array, is it possible that there exists an input such that no swap operation is needed to get the whole array ordered? Yes. Ascending order. Yeah. Think about ordered and ordered array. That's the case. Yeah. Yeah. Ordered array, the pivot already in place, right? The last element already in place. And you do not need to do any swap. Yeah. And all the remaining elements, other than the pivot, all at the left-hand side. So you do not need to move around those elements. Okay, yeah. So that's the case. Yeah. Yeah. Last question. If an array is too big to be loaded into the main memory of your computer, is it possible that one can design some special algorithm to get this array sorted? Yes. Yeah. So this story, I give you this special story when I talk about the motivation of merge sort. So, all right, yeah, merge sort. Go back to the merge sort. Yeah, I explain. Yeah, when the array is too big, we cannot load it from hard disk to main memory. Then we split. Yeah, we split it into many subarrays, but each subarray we can load it into the main memory. Okay, so we can sort each subarray in main memory without any problem. Yeah. After that, we use the merge operation to make all the array elements sorted. Yeah, so that idea. Okay, yeah, so it's possible. Yeah, yeah, so you can write a program. Yeah. So if actually we can design some algorithm to implement this idea. Okay, yeah, yeah. All right, so let me stop the explanation of quiz number 4 questions right here. Yeah, but I need to use the remaining time to talk about 2 very important questions. Yeah, because this review session is preparing you for the final. Yeah, so these 2 important questions closely related to some possible questions in the final. Okay, so I'd like to explain clearly here. Yeah. So when you see similar questions in the final, yeah, so you have the information here. Yeah. All right. The first topic I want to talk about, find the median of 5-element array. Find the median, how to find the median of 5-element array with the minimum number of comparisons. So this is a very challenging question, and it is, pretty important one in algorithms. Yeah, so we should know that. Yeah, but although its solution is very challenging, but if you have the right view on it, if you have the insight of it, you can get a solution quickly. Yeah. Here, I like to show you that view. Yeah. All right. So the question. Okay. Find the median of a 5-element array All right, so that's the original question. Here I do not need to say more. Yeah. That means we know when we see the question like this, we know some hidden meaning other than its face meaning. Yeah, so that is, we need to use the minimum number of comparisons to find the median of any 5-element array for the worst case. That's the complete meaning. Okay, here although we do not say, some of the sentences, but we mean that. Okay, all right. Here, so let's consider, all right, so solution. Here. Consider the 5-element array in this expression, x1, x2, x3, x4, x5. For simplicity, we can assume they are distinct. Yeah. But in real-world applications, you need to remove this assumption. Yeah. But you just make small adjustment. Yeah. So not too much work. Yeah. Here, let us assume distinct for our easier discussion purpose. All right. Yeah. All right. So when we work on it, we do our work in two parts. The first part 1, we collect some order information. We need to get some partial order information. Yeah. Keep in mind, we do not want to sort it. If we sort it, we spend too much work, some unnecessary work. We overdo it. We do not need to do that much work. So never sort it. Okay? Yeah. When you need to find a median, do not think about sorting in the first place. But under some special situations in future, for example, if you need to find elements in different positions many times, then sorting is a good option. Yeah, because after you do the sorting, you can use that information to get many elements in different locations. But if you only find a median, so then you should not do the sorting. Only one element. Okay? All right. So here, we do not want to do the sorting, but we need to get some partial order information. Yeah. So the step 1, okay, yeah, get partial order information. Okay, yeah. It would help us to find the median. Yeah, but partial, not too much. Otherwise, you overdo it. Okay, all right. What kind of partial? Yeah, here, these 3. Yeah. So this step we use 3 comparisons to get partial order information. Okay, all right. So let me draw the diagram. What 3 comparisons? X1, X2, do comparison. X3, X4, do comparison. Okay, all right. Here we make assumption. let's assume x1 is the smaller one. Okay, yeah, x1 small. We do an assumption. Okay, all right, for convenience. x3 smaller one. All right, because if it is the other case, you can switch to, yeah. So just a symbol notation. Yeah. All right. Then we do our comparison number 3, compare x1 and x3. Let's assume x1 is the smallest. Yeah, so x1 less than x3. Okay, so now you have 3 comparisons, number 1, number 2, number 3. Okay, yeah. After these 3 comparisons, yeah, so that's all we need to do. In step 1, we get a partial, we get a partial order information. Yeah. So what partial? Let me draw a diagram. Okay. Yeah. x1 here, but we also know x2 greater than x1. So we draw diagram here. And x3 below it, that means it's greater than x1. x4 below x3, it's greater than x3. This is the diagram. Okay, yeah. And the last element we have not touched it, that's x5. Yeah, we have no information about x5. Yeah, all right. So now we need to do that critical observation to get an insight. Yeah. Here, the very important observation we need to do to get an insight. Critical step. Yeah. After that, then the remaining work will be much easier. All right, so what's that? Okay. This insight related to the elimination method. Elimination method. So in this class, I talk about this method so many times. Here, we really need to use it. Yeah. And actually, this question, I gave you in different form before. Yeah, in homework or, some assignment. Yeah, so you can find a similar question before. Okay, yeah. All right, so here, which element cannot be the median with the information we just collected? Which element cannot be the median? So we can eliminate from the consideration. Okay, yeah. There is one element that is so special, there is no chance to be the median. From the diagram, you can see, right? X1 sit on top, okay? X1 sit on top. Yeah, so that means it is the smallest among the first 4 elements, X1, X2, X3, X4. X1 is the smallest among the first 4 elements. If we include X5, it could be smaller or greater than X5, but we don't know. X1 could be smaller, could be greater than X5. But we can say at most one element is smaller than X1, right? Yeah. So that is X5. 1, at the most 1, okay? At the most 1. Can you see if X1 can be the median, right? Median, the one in the middle, right? 2 elements smaller than the median and the 2 elements greater than the median. If one element is the median, you can find 2 elements smaller than that. But for X1, you can only find at most 1 element smaller than it, right? You cannot find two elements smaller than x1. That means the conclusion is x1 cannot be the median. Okay, this is the critical observation. With this critical observation, then you can do elimination, right? Because x1 is not a median. Can we eliminate it from the consideration? Yeah. So if we eliminate it, we simplify our situation. We do not need to consider x1 anymore. Then we can reduce the data size. We can make our question simpler. Okay, so that's the purpose of the elimination method, right? All right, so then stop step 2. Okay, step 2, the goal, find the median. Okay, yeah. Okay, all right. But this time we remove x1, right? Yeah. x2, x3, x4, and x5, we only need to consider these 4 elements. But in these 4 elements, the original median, yeah, because when we find the median, it should be the median of the original 5-element array. Yeah. The original median here, yeah, so I still write this median, okay, our original median equals second element here. Okay, yeah. Because we know x1 is at the left side of the median, right? So we take away one element at the left side, left-hand side of the median, then the median becomes the second element in the remaining subarray, right? Yeah. So our question becomes find the second element in the current subarray. Okay, all right. But so let's look at the current situation we have. We have x3 here, x4, because we already know x4, we already know x3 smaller than x4, and x2 here, x5 here, we do, x5, yeah. But we do not know which one is smaller, which one is bigger, okay? Yeah, so we need one comparison to get x2, x5, which one is bigger, which one is smaller, all right? So that's our comparison number 4. After the 4th comparison, we know which one is bigger, which one is smaller, between x2 and x5, okay? Yeah. Here, for simplicity, yeah, let's assume x2 is smaller than x5. Otherwise, we can swap, right? Yeah, yeah. We can put the smaller one above the larger one, yeah, in the diagram, okay? All right, yeah. So now we have this case, x3, x4, this comparison, or that's number 3, okay? We do not need to do a new comparison, okay? And now, number 2, right? Yeah. In our old diagram, this is the comparison number 2. We already have it. All right. And x2, x5, that's the new comparison. Okay, number 4, x2. Okay, all right. Then, comparison number 5. Okay. Which one is smaller, x2 or x3? Yeah. So we can assume anyone, because similar situation. Yeah. All right. So let's write x3. All right. Yeah. All right. So after 5 comparisons, we know x3 is the smallest among the remaining 4 elements. Okay. Yeah. But that's what do we need? What we need is the second smallest, not the smallest. We want to find, all right, second smallest, not second largest, second smallest. Okay, second smallest. Yeah. So it cannot be x3, all right? So the candidate, let's look at the candidate. What are the candidates to be the second smallest? Okay, yeah. First, x3 cannot be the second smallest, right? It's first smallest. Yeah. So the candidate for the second smallest, can x2 be the second smallest? Yeah. Can x4 second smallest? Can x5 be the second smallest? No. Yeah. Here x5 cannot be second. Why? Because x2 is smaller than x5, right? So x2 should be considered the first before x5. x5 is greater than x2. So x2 has higher priority to be considered than x5. Think about that logic. Okay? Yeah. In other words, another way to see it. Yeah. How to see the second, yeah. So first smallest, no argument, right? First smallest. Yeah. Done. Yeah, we know which one it is. So second smallest here. Second smallest. Yeah. Here you can see, if you do observation, what are the candidates? Here we look at the candidates for the second smallest. What are those elements we can consider as the candidates for the second smallest? Now here, the observation, look at our diagram, that would be direct loser, direct loser to x1. Okay? Direct loser. Yep. So you know the meaning. Those elements were beaten by x1 directly. Okay? x4 is beaten by x3 directly, right? x2 is beaten by x3 directly, but x5 is not beaten by x3 directly, right? Think about x5. We know it's greater than x3, but indirectly through x2. Yeah, x5 is greater than x3 through x2 indirectly. But here, for the candidates, we only consider direct losers to x1. So only 2 candidates. Yeah, x2 and x4 here. Yeah. So the question becomes, in the last 2 elements, x2 and x4, the last 2, we need to do one comparison. The smaller one would be the second smallest. Yeah. So our comparison number 4, x2, x4, we need to do last comparison. That's our comparison number 6. And the smaller one would be the one we need. That is the median we want to find. So you can see the answer 6 comparison. So at the end, the answer is 6 comparison. Okay, to find the median. How to do it? Yeah, so this slide, you see how to do it. Okay, yeah. Try to follow the whole story, the analysis. It's hard. It's not easy to follow. Yeah. Yeah. But if you follow the logic carefully, you can get it. You can get it. Yeah. Okay. Yeah. All right. Yeah. So for the conclusion, to find the median of a 5-element array, the smallest number of comparisons we need is 6 for the worst case. Yeah. Yeah. Okay. Yeah. That's the conclusion. Yeah. All right. So then, yeah. Then I want to, yeah, because we do not have much time left. Yeah. So we cannot do another question, but I can say something. Yeah. Yeah. So here, we know median of 5, right? So here, we just did median of 5 with 6 comparisons. All right, yeah. Then another related question is sort 5-element array. We know sorting, we need to do more work than finding the median in general, okay, in general. Here, our expectation to sort 5-element array, we should use more than 6 comparisons. We need to do more work, okay? Yeah, here, let me give you the answer. 7 comparisons, just one more, okay? Just one more, we can sort 5-element array, 7 comparisons. Okay, 7 comparisons. Yeah. Yeah. One more, you can get it sorted. Yeah. How to do it? That's another challenging question. Another challenging question. Similar to finding the median. Yeah. Similar to finding the median. Yeah. But slightly different because you need to sort it. Okay? Yeah. Yeah. All right. And here, the topic 8.3 here, I want to talk about lower bound to sort an array. Yeah, to sort an element array. Lower bound, there is a formula. Yeah. So I will explain it next time. Yeah. Because this is another relatively long story. I need to talk about that. Yeah. Yeah, because these 2 questions, yeah, the knowledge here for these 2 questions, important for you. Yeah. So you will complete this course quickly. I feel you should know this kind of knowledge after you complete the course. Okay, yeah. So that's the reason in the review, I put this content here. And in the final, I may give you similar questions related to these 2 topics. Okay, yeah. All right, so let me stop right here,